Hello. Welcome to this first in a series of tutorial videos on ISETCam and ISETBio. My collaborator, Brian Wandell, who's here on the call, is planning, he and I will be recording these over the next while and posting them. And we're glad you're either here in person to watch as we do it and ask questions and interact, because that would be great, or are watching it online, and we'll look forward to the possibility that you use these tools, which we're eager to have you do. So the goal of today's video is going to be give a little bit of an overview of what we might call a core calculation that can be done in ISETBio, and I'm going to overview here with a few slides what those pieces are, and then we'll switch to some code and go through a little tutorial example of how that calculation can be done in ISETBio. And the goal today is to give that overview of what I, again, call a core sequence and explain it. And then in the next tutorials that we haven't recorded yet, but we will, we'll unpack each of the pieces of that calculation in more detail. So the basic calculation we want to talk about today is one where we start with basically a red, green, and blue image, a typical monitor image, and convert it to what we call a scene, which describes the image in physical units as a function of wavelength at each pixel of the image. And then how that scene, which will be the input to the calculation, can be converted to a retinal image through a model of the objects, and an object in ISETBio or ISETCam, the ISET system that describes the object. And then that gives us a retinal image, again, as a spectrum at each pixel. And from there, we'll describe a mosaic of retinal cones of the three cone classes, L, M, and S, and compute the very first stages of the visual representation, which are the rate of photopigment excitations in each cone in the mosaic, or if we fix a duration, the number of cone excitations in response to the stimulus over a fixed amount of time. So that's what we're going to do. And just to say a little more about the calculations before we turn to it, this just unpacks the scene object a little bit. We go from there through the optics, and the optics are described in these initial calculations by a polychromatic point spread function. So at each wavelength of light, we use wavefront optics measurements taken from the literature that we have as part of the ISETBio system to compute a point spread function at each wavelength, where if we consider this the center of the image at the retinal location we were considering at a particular wavelength, the point spread function is going to describe how much little point of light is spread out across the retina. And quite importantly for these calculations, we model a chromatic aberration of the human eye, which causes the point spread function to get quite a bit larger as you move away from an in-focus wavelength, say 550 nanometers, either to shorter wavelengths or to longer wavelengths. We then use that model of optical blur or optics formation together with the size of the eye and the size of the pupil and the absorption of light by the lens of the eye to compute the image that arrives at the retina and is the kind of the light that's then tickles and stimulates the photoreceptors.
So, David, before you move on, and
sure.
the spirit of keeping this thing going
Great.
one of the things that way you started is with this notion that I think is really important for psychophysicists, which is you often start with something on the screen. But we also have ways of starting with very general images. So this is an important case, particularly for biologists and psychophysicists, but general images is important. The second thing is, in that image right in the middle of your screen there, the massive, so one thing, implicit, not shown in the image, but we know exactly how far in microns each one of those images is spread. And that's something that's important to David. Nicholas is on the call too. And we're always keeping track of units throughout this very intensely. And the other thing, for me, maybe for some of the people listening in as you go through this, Dave, is that the shapes of these point spreads are just, they're really structured, and they've got these little bumps and they change in size and so forth. And that's not something that, when I started as a graduate student, that was known. But thanks to these measurements with adaptive optics that Williams and Thibos and Dave was part of early on, we really now know a lot more about those point spread functions, and that's kind of cool. So
Great. So I'd say to people who are here today, first of all, Buddy, and anytime you want to expand, I think we can let this go as long as we want in terms of the recording, and it's great to have it be interactive. And particularly if I say something that's incomprehensible and could clarify, stop us and we'll try to unpack it. Again, I maybe just riffing on the theme that Brian started here. We are in drawing on data in the literature, and one of our goals in this project, in addition to the things Brian laid out, is to kind of integrate measurements from many labs together into a kind of, we'll call it coherent computational software environment, so that not only the nature of the computations, but the data that drive it are available. And certainly measurements of the optics from other labs, not ours, are key to the accurate computation of retinal image. Okay, then so we have a retinal image, and then again, we know a lot about the cones from work done in the field over many years, and therefore, and what's shown here are the spectral sensitivities of the actually the absorption spectrosensitivities of the LMNS cone photopigments, the long wavelength sensitive, middle wavelength sensitive, and short wavelength sensitive photopigments. When we use those in calculating the excitations of photoreceptors, and when we put particularly the default design matches the CIE standardized cone fundamentals for the fovea, which are based on the work of Stockman and Sharp, very carefully working out the details of the cone fundamentals, and they match when you take into account the lens absorption that we build in, and also macular pigment absorption and the density of the photoreceptor pigments that contain these three pigments. In addition, the packing.
So Dave, there's just something who might be looking at that prior picture.
Yeah.
In this picture here, it doesn't have the lens as part of it. And many people might look at this and think, whoa, that blue is really high at 400. And but when you do the calculation, the lens shows up, and that takes all that short wavelength stuff, really knocks it down.
Correct. The other key data that we use in this initial part of this calculation is a map of where individual cones are. We synthesize these mosaics with an algorithm that Nicholas Koteris, who's on the call, developed. And that's based on matching the cone density data. The algorithm will work with any cone density data. We're using data from anatomy anatomical measurements reported by Christine Curcio and her colleagues. And there are a lot of interesting features of the cones in the human eye and the fovea that we try to capture. They are most dense right in the center. You can see they're a little smaller and grow even over about 1 degree, which is shown here. The S cones are sparser than the LNM cones. The LNM cones are distributed almost randomly, and we build synthetic mosaics that match those properties. And then given the mosaic and the cone spectral sensitivities and the retinal image, we are able to compute a map of the photopigment mosaic excitations for a realistic model of the human retina. So that's the calculation that I'm now going to turn to and show you how that would look in a basic ISETBio script. And we can go through that piece by piece and unpack some of these ideas. But these slides, I hope, give you kind of an orientation to where we're going to go with it. So I have up here Matlab, and I have this tutorial RGBImageToExcitations, which, as the description says, is going to take an RGB image and a typical display characterization and compute from that the retinal image, and then from that the photopigment excitations of a patch of retinal cone mosaic. It's an overview tutorial that illustrates a core ISETBio processing pipeline from stimulus to the initial daylight visual encoding. And it's meant to convey how this would kind of feel and look, and expose a few of its parameters as a point of departure for calculations. in tutorials that we'll go on to, we'll unpack each of these stages and the elements that make up this chain. If you're new to ISETBio and ISETCam, I'll just say a few things. First of all, you need these two GitHub repositories. You need to get them and unpack them and put them onto your Matlab path. ISET stands for Image Systems Engineering Tools, and the CAM version contains our code for representing scenes and displays and computing in general images at the sensor plane, be it a camera or a retina. And then ISETBio contains routines that work with the ISETCam representation, but are focused more on the human biology and biology in general. Indeed, we can do some work with other species as well. So you need to have this installed. There are instructions at these websites on how to do it. This tutorial is currently in this folder, but we'll update. We're working out exactly where it will live in the long run. And if you happen to use the toolbox, which is here, you can configure your whole system in one set, even if you haven't installed anything but the toolbox, just by running this one command, which I'll do to make sure I'm in the right place in my own Matlab. It's just getting all the pieces that I use when I work.
So let me add that's great. Let me add a couple of things. When you go to the either ISETCam or ISETBio websites on GitHub, there's a wiki page, and the instructions are really make sure you get to the wiki. That's where the instructions and more information is. And the second thing is everybody I know and like, not just Dave, but John Winnower and many others use this toolbox. I might be like the only person who doesn't use it, and I apologize for that. But nonetheless, I know many people who like it and use it and see it as a time saver for them. I've just got my old ways, and I haven't moved into the modern age on that.
Your old ways is setting your path? Is that what?
Yes.
Yeah. And you by no means need to use it. I was just trying to give a little pitch here.
Yeah.
Okay, so I'm updating this as we go, and so typically in any script we would initialize. I'm going to just select individual cells here and execute them as we go through. So I'm clearing everything out and calling a simple initialization. As Brian noted, we work in physical units, and we try to work in the spectral domain at the beginning of the representations, because both in particular blurring by pre-retinal absorption and getting the optics right in chromatic aberration really requires a spectral representation. You can't just start with RGB and not know anything about the spectra to get there. And so we, at any given time, define as part of the calculation what wavelength sampling we're using. I'm setting up here between visible spectrum between 400 and 700 nanometers, 5 nanometer sampling, which is pretty reasonable to use. And the first thing we would do in this tutorial, we're going to start with an RGB image, and we're going to create a scene object, which is a sort of core ISETBio, ISETCam structure. And just as an aside, this is implemented not as a Matlab class, but it has some history to it. It's a structure underlying it with functions that act as methods on this structure. But we think of it as an object in the way we use it. And what I'll show you here is some basic parameters to set up, and then we'll create the object. So we're going to start with an RGB image. I'm using one that's available within the packages. Zebra, it's a picture of a zebra, it's a JPEG. All of these could be substituted into this tutorial and it would work, so you can experiment with those. And in order to get a spectral representation, we're going to treat this image as having been presented on a calibrated display where we know the spectra of the red, green, and blue channels. We know the gamma function of the display, the input-output nonlinearities for each of the channels, which are contained and described in a display object within the ISET system. And this is one that we happen to have from measurements that were made that's stored and available. There's several others you could swap in, or if you're a psychophysicist and you have your own calibrated display, it's easy enough to make a display file for that. Since we want to stay in physical units and physical sizes, as Brian mentioned, we'll define, since it's not part of a standard image, how far away is the viewer from the display, what's its field of view, which in some sense then determines its physical size of the display at this distance, and what luminance do we think the mean luminance of the scene is, so that we're now locked to physical intensity, which we specify in candelas per meter squared. So these are some parameters that allow us to go from an uncalibrated image that we might want to work with to a calibrated version of it on a calibrated display for purposes of computation. So I'm going to set all those variables, and now I'm just going to read it, and I'm going to set it to some size, which here I'm just I think not changing, but if you wanted to up or down sample it before you work with it, this would do it. This is standard Matlab image processing toolbox code. If you didn't want to do it, you can just comment out that line. Okay, we have that. Inside of our package is a routine that creates an ISETBio scene from a file. We're going to tell it the name of not the name, we're going to give it the Matlab image. We're going to tell it that it's an RGB image. We're going to give it the display that this is defined with respect to, and the wavelength sampling, and we will have, just like that, an ISETBio scene object, which we'll talk a little bit about next and look at a little bit in the variable SC. We like to access properties of scenes, not by going and looking at the structure, but by using set and get methods. And so before I go further, I'm going to do a few things here that aren't done by this. We're going to give it a name. That's just something that one could look at to refer to it. But in particular, we're going to specify the distance that we defined up above, the field of view, which is the comment will say it's the horizontal field of view in degrees, and the mean luminance in candela per meter squared. These are all sets that I can do on the scene. And so I'll do those. And then I'm just going to check when I get the field of view horizontal, it computes the field of view vertical inside the scene by the aspect ratio of the image. And so I can get and print out the size. And there it is. It's 2 degrees wide because I asked it to be. And apparently it's 1.3 degrees wide because that's the aspect ratio. Now we haven't looked at anything yet. And so let's just look at it, and then I'll pause to see if there are comments or questions. But we have a nice GUI that allows us to examine scenes, and we put the scene to make it available for that GUI by the IE add object command, and then we open up a scene window, and we'll be able to examine the scene that we've created. Okay, and here it is. Anybody want to ask questions or comments at this point? This is the first step of the calculation. I was going to show a few things we could do with this window next, but let me pause for a second.
I just have 2 comments. One is in line 81. I don't think you mentioned what is the empty argument. I believe that's the display that you would like, the main display you would like to have.
I don't know what that argument is. Are you could have put this number in there?
If I'm correct, that's the main display, main luminance, but I'm not sure.
Yeah, okay. So I could have done what I did in 2 steps,
Yeah.
apparently by 1, and for whatever reason,
Right.
I'm in the habit of using this routine.
Just because somebody might wonder what that is.
Cool. Yep.
And
by
then,
the way, if we had not remembered that, and no one had asked, there's a good chance we could help scene from file and find out something useful. And it might, and that's true for most of our routines, we try hard in documentation. Input data image type, yes. Mean luminance is an option. These are all optional arguments, which means some default will be filled in. Since I was going to set the mean luminance later, I just left it as default. These are things we can unpack more in later tutorials. And then you had a second thing, Nicholas?
the other thing is in line 93, I don't think you need the transpose to fill the width dex. It's just a scalar.
Oh,
Good on you. Good catch.
All right. All right, thanks.
I've got something at that level. Which is I always used to do this, i.e. add object and scene window, and it drove me crazy. And so now I just those two things are done if you just do scene window open paren SC also.
Oh, how wonderful. Because I can never remember what the first one is. I have to always go look it up. All right, great. So it's getting better by the second.
Do you want to evaluate and see if it works?
Yes,
See-
Yeah.
No, I'm not that. What I wanted to do is go find the window, which is presumably here somewhere. Oh, I guess I'm gonna have to do it because somehow it got closed. All right, so we're gonna execute this again in this new form. Here it is.
Hey,
Great. And I'll just note a few things. There are lots of features about the scene that you can read off here, like the field of view, how many rows and columns does it have in pixels, the height and width in millimeters, which is determined given that I set the field of view by the viewing distance, but there it is. The angular resolution in degrees per pixel or sample.
Hey, David,
Yeah.
Click on that, so it'll get bigger, and then it's
Then we
easier
can see it.
to see in the video.
And great, the wavelength sampling that we used, what the radiance was in these units at 400, looks like 450 nanometers. Is that what that is? Yeah, peak radiance at 450 nanometers, the mean luminance in candelas meter squared, something about the ratio of min to max in probably units of, well, is that the
Got to be photons, yeah.
photons, and the depth range,
Actually, I take that back. It's a dynamic range, so it's a ratio.
the ratio. There must be something
blackest
very
thing.
dark somewhere,
Yeah.
which,
I
and
think I'm going to change that. More recently, I've been looking at the 99th percentile to the first percentile. I'll add that in at some point.
one thing, since you have this open, I don't know if you're going to talk about this later, but you can change the illuminant, and you had D65 as the illuminant, but one nice feature of this is that you can change if you want to.
On the GUI?
Yeah.
Oh.
Yeah, both on the GUI and in the script.
I don't want to talk about that now because that's something we might unpack in the context of what that would mean, in a later tutorial.
Yeah.
What I did want to show was that you could look at things in here. So for example, and again, we'll do more of this later, but you might want to see, this is different from when I practiced it. Or maybe I wanted to do plot. This is what I want to do. Okay, so I can make a little plot and it would tell me, I guess this is the average of the spectra within that region. Is that what I successfully did?
Yes.
We'll unpack later, but you can see lots of things about the underlying data in this window. And then there are also ways to get all these pieces programmatically. And one of the reasons I'm less facile with the window than others on this call is because I mostly do it programmatically. Okay, so we got the scene. This is an overview tutorial. There it is. We created it from RGB image. And now we're going to set up the object so we can compute the retinal image. And we call that the OI object for optical image. In the camera world, that's probably a better name. In the ISETBio biology world, it's a synonym for retinal image. And we produce a basic optical image by creating one. OI equals OI create, and we pass in that we want the human defaults, the properties of this optical image for a typical human eye, which I'll talk about a little bit more, some of its properties below. And then we're going to make sure that the wavelength sampling of our OI is matched to what we set up at the top. So I will do those two things. And then I mentioned in the slides that we use wavefront optics to produce a polychromatic point spread function. So this loop of code, and there's a comment that says probably there's an easier way, but this exposes one way of doing it. I'm going to loop over 1, 2, 3, 4, 5 sample wavelengths. And for each one, I'm going to make a call to OI plot on this OI and ask for the point spread function at a particular wavelength to go into with the no figure, whatever subplot I just set up. And then I'm going to use that to get the data out of it. And I'm going to mesh the data in order to give me a picture of the point spread function. So this loop, with any luck, will produce a little mesh plot of the point spread functions at each of these wavelengths. And so 550 nanometers is in focus, and you can see the light energy from a single point is highly concentrated. This is minutes of arc on the retina as the axis. And then as you go to longer or shorter wavelengths, the point spread function becomes broader. So this is a mesh plot view, the kind of thing I showed there in that first set of slides for the optics. And then we haven't yet computed anything. We've just created this OI object, and but we'll then compute. So the OI compute command is going to compute it, and it's going to use the polychromatic point spread function. And then as came up earlier, we're going to build in, because it's part of the transformation from the light in the external world to the retina, the spectral absorption of light by the lens, which absorbs more in the short than in the long. One little subtlety is at the edge of a scene, if you're blurring with a point spread function, to compute a value at the edge, you need to assume something about what was outside the edge. And this in this OI compute function, which takes the optical image object and the scene object, computes the retinal image and stores it back in the optical image object. We tell it that we want to pad outside the image with the mean image value. There are other choices there, which we could discuss in a future tutorial. So I'll do that calculation pretty fast, not infinitely fast. And then just to do one little example of many, and you could do help OI get or help OI compute to see more about this. I'm going to get the size of the optical image in degrees, which is inherited from the image, but will be a little bit larger because it had to be padded by this mean value out a little ways. And this compute routine judges the size of the point spread function and pads sufficiently to blur out to the edge, but the padded optical image is 2.5 by 1.6 degrees. Can I do OI window OI?
You can.
Okay,
And there's going to be one other thing, but do this first, and then we'll do the next. Then I'll say the other thing. That's good.
Okay, so now we've got a window and a GUI that lets us explore. And again, I won't do a lot of exploring here. The retinal image in the same way that we explored the scene originally. And one thing you'll notice is, well, this is yellower than that. And the first time we looked at this, can that really be right? But it is, because we are modeling the absorption of short wavelength light by the lens, and then we're just rendering this kind of metamerically on a standard monitor. Presumably we can do a similar thing here, and here are some properties of this thing. It used shift invariant convolution near the fovea to compute the blur. It was based on human wavefront measurements, and we haven't talked about the options there. That'll be in a more detailed thing. Size of the eye parameters that were involved. For example, the eye length here is 17.2 millimeters by default for the human eye, with a 3 millimeter pupil, which corresponds to 5.7 F number. The optical image inherits its name from the scene. We computed with one of the particular ways we have of doing this, et cetera, et cetera. So again, you can come and explore from the menu here features of this image that we've now computed. And again, as you're seeing over here, and as Brian emphasized, we're still working as much as we can in all cases in physical units with all the pieces of these calculations. So again, I'll take a pause before we move to the cone mosaic.
Yeah, there's one thing that I'm doing a lot of now, back to the calculation, if you don't mind, just to run it. And I do this a lot. When you do OI compute, a little bit down there, there's a new parameter that Jen Yi and I use all the time. Comma, single quote, crop, CROP, and then comma afterwards, yeah, and then true. And run it again, Um,
I have a
And-
feeling I know what this does.
yeah, then
All
bring
right,
it.
so now it's back to the image size. So although we padded out at the edges, apparently, now we're just going to look at the points that correspond to pixels in the original.
Yeah, run the OI window. That'll be,
And
that's
then we'll do this and we'll see that.
right.
And great. Okay, and now it actually has this nice feature, probably if I make the windows the same size. Well, no, not quite,
Yeah,
but getting there.
So that's not the default to crop.
it is
Oh.
not. The default is to show the pad.
I see.
But you know, you get to vote. So
Yeah, I would vote for it to be the default, but yeah.
I've been using crop a lot. So
Yeah.
Okay, great. Okay, so now we've got a retinal image, and we're going to move on to defining a cone mosaic that will sample that retinal image and compute the cone isomerizations, or which is spelled wrong, and which we often call the excitations. Maybe I should call it the excitations. But they're synonymous from our point of view. So we're going to get a set of, again, we're going to get a set of default, the cone mosaic, the object is called a C mosaic, which I'm going to create in Matlab down here, the C mosaic object, which describes the cone positions. At this point, by the way, if you were interested in camera simulation, we're now diverging from sort of common things between the ISETCam and the ISETBio pieces and specializing in something for biology, namely a mosaic of cones. And there are a lot of features of the cone density, the size, macular pigment, many things that can be controlled. And just to sort of illustrate the idea that there are many things that can be controlled, we can get all the parameters that this thing would take. And again, I won't go through their meaning here, but just to illustrate that there are many of them, lots of features of the cone mosaic that can be controlled. And but they have reasonable defaults. So if you just ask for C mosaic params, you're going to get parameters that make sense for the human foveal retina. We want to say, how long do we think we're going to calculate the excitations over? This is in milliseconds. And so
is that right? Is that in milliseconds or in seconds?
it's milliseconds.
No, it's seconds.
That's 100 seconds?
Yep.
Okay, well, all right, I stand corrected. We're going to do 100 milliseconds. Because that's what I meant to do. And maybe I should, anyway, it's in seconds. So there we go. Thanks for the correction. And we're going to say that we want to we're going to put this mosaic right in the fovea. So 0, 0 eccentricity. And we're going to make it the same size as our OI size, which we had up here computed. So it's matched in size. And we're going to make the number of microns per degree in the C mosaic match up the number of microns per degree that belong to the retinal image. And that's because the default parameters of mosaics about eye size may not necessarily have agreed with the default parameters in the optics, and this just handles that possibility. So I'll get all those parameters defined, and then I create a C mosaic, which is going to take a second here because it's loading in some data, and also calculations with the C mosaic depend. We use the Matlab parallel processing toolbox, and that was not fired up on my computer, and that takes a little time to go. So while that's loading up, again, I can take any corrections, additions, elaborations, questions.
Yeah, I have a suggestion. So the microns per degree in the cone mosaic is being calculated depending, the default value is being calculated depending on the eccentricity of the mosaic using Watson's formula. So one thing that I might do different is first generate the mosaic, then get the microns per degree and use that value to set the correct distance per degree in the optical image.
So we could do the dependency in the other direction.
Yeah, I think that might be a little more,
Taking a good
if you
point.
want to take into account the variation with the centricity in microns per degree.
For a lot of these things, I think it's important to have them, well, it's good to have them right. It's even better to have them consistent across the different pieces. And
so the other thing, so that's interesting, but let me get and important, but also a little complex. Let me make a kind of a trivial thing for people who are just beginning here. Do you notice that David used several times now this OI get, OI set, things like that? And I guess we should probably have commented that if you wanted to know all of the different routines that have to do with the optical image, yeah, just what you're doing, you could type OI tab, and there's a whole bunch of them.
Mm.
And for any particular object, OI's been around for really a lot of them. But for any particular object, you can always create it. You can set its parameters. You can get its parameters. And there's going to be a plot routine that goes with it also. So those are kind of dependable. Yeah.
And I noticed, Brian, that your plot routine gives you back data if you want to.
Yes.
That's something that I was thinking about for the C mosaic and for the ganglion cell mosaic. I might adopt that. I don't know.
And I think we both in these plots, it does return data. I think you also stuff it into the window itself, right? We set user data, and that's true for OI for all these plots. That the data, if you don't return it, it's still in the window. You can get it from the window.
Right.
Great. Okay. I will say that again, our goal in this, we will try to, and it can be a little bit intimidating to look at all those things you could do with an OI.
Yeah.
And that our goal here will have a kind of separate tutorials that unpack the scene and the OI and the C mosaic and the wavefront optics and the displays that will kind of go into more detail of things you could do with each one. I'm going to keep moving here for today. In part because I'm going to miss my train if we don't finish soon. Which I could do.
You're going to visualize it now, right?
Yeah, we're going to visualize it. So this is a method, and by the way, the cone mosaic, C mosaic object is implemented as a Matlab class and actually does have methods. But this is actually now a picture for the patch of mosaic that matches this image size that we're computing with. Of the actual cone locations in this particular one. And it tells us in the title that there's 60% L and 30% M and 10% S. K is a thing you can ignore, and that there are 26,927 cones. And this plot is as a function of degrees of visual angle. So that's one of the many visualizations available. Something else, well, something important that you can do is now you can compute from the OI, you can compute the excitations of all those cones. And you can get two versions of that computation. One is the mean response to the amount of light coming in, and the other is a noisy instance of the mean, where the Poisson noise that causes trial-to-trial variability in the number of excitations has been added in. So I'll do that computation or set it going. It's pretty quick. And there you go. Now we've computed the cone excitations. That was our goal for this whole tutorial. But we might want to look at things a little bit. And the cone mosaic, C mosaic object's got a plot function, and we could plot the excitations. We're going to plot the noise-free excitations, and the label cones, I think, is going to cause them to be plotted in, well, we'll see what it does. Characteristic colors. So here is a rendering of the cone mosaic, and you can see the zebra in there, where each cone is red, green, or blue, depending on whether it's L, M, or S. And then the intensity of that has been modulated up and down according to a intensity scale for each one to give you a visual sense of how the mosaic activations have been sampled by the retina and how much each cone is has been excited. So that's one of that. And again, there are many different plot options which we'll unpack at some point in the future. The visual is, but here's another one. You can get the list of params that the CM visualize method, which is another way to see things works. I'm going to set up another one here, which will do a grayscale version of the noisy excitations. Now we see that. There's quite a difference in the overall, and this actually came up when Brian was talking about dynamic range. It looks rather low contrast version of the zebra image. And that's because the S cones are quite a bit dimmer than the LRM cones, and because there's some very dark pixels. You could get the activation range for this particular thing, and instead of going from 0 to the maximum, you could go from the 5th to the 90th percentile by just getting that little vector and redo that visualization. And now you would see the zebra more clearly because the range over which the plot is happening isn't as distorted by a few extreme values. So there's another way to look at the result of this calculation, which really is now the first neural stage of the initial visual encoding. And we've gone all the way from the image to that. We can plot lines through the we could plot, horizontal line through the image. And what have I done here? I've done a separate plot for the L, M, and S cones through a horizontal line at y = 0, taking a little band. Every cone within that band, I've plotted it as a point, and its excitations over that 100 millisecond time are shown here. And so you see some cut through the structure of the zebra seen by the 3 cone classes, and you can see that the S cones are sparser. And also these numbers run from 0 to 250 because of the filtering of short wavelength light by the lens. The S cone excitations are considerably down from the kind of 0 to 3,500 or 0 to 4,000 range of the L and M cones. That's
shocking, isn't it, how photons the S cones are?
You might wonder, where are those cones if you wanted to start finding them, or what were the cone types? This list, I should say that the excitations are just in a list, because there's just a list of cones. So there's a lot of them there. 26,000 just got printed out. But they all have positions which correspond to them, and that would be in, I think I computed this list. So it's going to be the same vector. These are the positions, I believe, in microns, right, Nicholas?
Yes, yes.
You can see it in the name right below. CM cone RF position, micron.
Yes, as the variable name suggests, these are in microns.
But by the way, this is a thing that David and Nicholas and I are always back and forth about the lengths of the variable names and about how much information we pack into it. This is good.
Yeah, this one I tried to restrain myself. I knew you'd be looking at this. And then of course each cone has a type. And the types are 1, 2, and 3 for LMS. I should maybe expand this respectively. And so from if I wanted to go in and find all the L cones, I could find all the ones in this list that were 1, and I could select out all the L cones responses from the other list that corresponds to it. And the last thing apparently I could do here is pull out the LMS images as a density full map. So I think without the cone sampling, but with the properties of the cone absorptions, it happens this returns them flipped up down from the way you might normally look at it. But here is a rendering of that zebra image metameric, but with the cone spectral sensitivities taken into account, rendered back on this monitor. And as you may remember, the retinal image looked yellow because of the absorption, and that's also true of this rendering, but it does give you a kind of sense of the continuous information recorded by the three cone classes if you were to interpolate in between the samples, or actually if you had sampled them at the pixel resolution of the optical image, but with the appropriate cone spectral sensitivities. This is just a way of looking at it. So that is the end of this tutorial. I'm going to stop my share and bring us back to our smiling faces. But that gives you an overview of sort of, in some ways, I'd say how easy it is to do really quite a complex calculation from image all the way to cone excitations in a very biologically realistic way that you could then use for other calculations or to start manipulating pieces. And in the future tutorials, we'll begin unpacking how that goes.
And you know, sort of, so this, we could flip it from here, but I was going to say David's Buchians has this goal of there's this multiple sclerosis related disease, so that over every cone there's some there might or might not be some molecular buildup, and he would like to model that. And what David just showed you was that you do have, for every position, you've got a cone response. And even if we didn't build it all the way in, we could, from what we have right here, we could take all those cone responses and scale them depending on the images you have of people's eyes. You know, give me a position, I'll tell you the density, I'll knock it down by that density. So you can see it's like right there in front of us. We just, to make it happen more smoothly, which is what Nicholas will help with, because we think it'll, you know, we might also use it for blood vessels, we might use it for other things. We're right there. You know, it's going to happen.
So you've stopped recording?
No.
Oh.
But we could
We
maybe
can edit.
And
Yeah.
And we'll edit things out, but I just
we might end it a little earlier, or we might just leave our friendly chat for the week.
who knows what we'll do.
Yeah.
Anyway, this is great, David. Thanks for.
Yeah, no, this is great. I had one question. You know, the retinal image that you showed at first with just the cone mosaic, it looked like it was darker in the middle, like there was this shadow casted. What is that?
So there's an S-cone free area in this. Well, first of all, they become more dense. So when you render it,
Yeah. Okay.
Also, there are no S-cones in there, and that affects the way it looks in our vision.
I see.
But also,
if you zoom in, they look just as bright as the peripheral ones.
But the point that I learned this from Nicholas as he was doing these calculations, what a huge effect this is. The aperture in the very center is much smaller, even when you go just a degree out, or by the time you get 5 degrees out. The aperture of the cones starts small, gets bigger and bigger and bigger.
Oh, I see.
So the number of excitations is much smaller in the fovea than it is in the near periphery, and that's why it looks darker when you see that whole image in the fovea. It's because the cones have a smaller aperture, and they literally are collecting fewer photons.
Okay.
Oh, I thought Josh was talking about the cone mosaic itself, not the excitation.
I was just thinking of the rendering. I was trying to understand, you know, is that a shadow? Is that the macular pigment or something like that? It just looked like, you know, the shadow that was circular.
And the macular pigment is in the calculation as well, but it does not change. That was a 2-degree image, so it's affecting. It varies a little bit over that, and we do have the ability to calculate the space varying macular pigment. But I think, as Brian said, the big effect is the change in cone apertures, which is enormous over the central retina.
Yeah.
Interesting.
Yeah, and you know, Jen Yi and I are constantly worrying about sensors that have different pixel sizes, what you can do with that. And so here you are confronting the human retina, where the pixel size just varies all across the place. And that means the reliability, the spatial sampling, all kinds of stuff. It depends. I mean, we would consider the kinds of sensors that match the fovea compared to the kinds of sensors that match the periphery. You would never use them for the same commercial product, right? And yet they're all in there at the same time in the eye. It's interesting.
And do you see any kind of matching of the optics to that? Like if you were to plot something in the optical image, would you see it corresponding is, you know, a good fit over the rendering of the retinal?
No,
I don't know, kind
no,
of
we've
curious.
looked at, so Nicholas is really the world's
Yeah,
expert.
good fit is in the eye of the looker, but
Yeah, you can see that the point spread function enlarges quite a bit as you go toward the periphery, and also it becomes a lot more elongated
Mhm.
at sort of like predictable orientations as you go around the
Oh,
foveal
cool. That's
periphery.
cool.
So
That's-
it's yeah, the optics are very interesting as you move in the periphery. And actually they become a dominant factor on how the receptive fields look in visual space.
But I would say, I think what David said is also true. It doesn't match or not. Joyce is nodding because, you know, you're feeling satisfied as if they match. And qualitatively, they're changing in the same way.
Yeah.
But I wouldn't say they were a close quantitative match.
Right.
No.
Well, you know, you're generating these pictures that are also just going to be great for teaching. Like this thing that you just said, Nicholas, would be really cool to, you have all that information about how the point spread function changes with eccentricity, it gets elongated. Be kind of cool to have that visualized. And so you had that data, you could visualize it in different ways.
The cone mosaic can visualize the point spread function that it works on. So yeah, so you can see the point spread function on top of the cones
Right.
at every eccentricity.
Oh, that's cool.
Yeah.
let me just say, if
cool.
we decide not to cut the recording off before this part of the conversation, we should say there are lots and lots of tutorials associated with the ISETCam and ISETBio repositories, and in there are tutorials that show exactly what you're asking about. Finding them is another matter, but they're there, and it's quite interesting to look at these.
And you know, we'll discuss what we do with this video, but my impression of undergraduates or graduate students is they're very good at going at double speed and sliding the video along to cut out anything they don't want to hear. So I'm not sure how much time we should edit. We should just.
But it's also easy to edit it too.
Anyway, we should cut it off now because I am going to
Okay.
go catch my train. And,
Thanks. That was fun.
We'll be back next week with another one. So,
Yeah, we'll figure out what's on next week. Thanks a lot. Thanks for coming, David.
Bye.
Bye.
Bye-bye.